Yeah. One of the pretty pictures. Yeah, this is, yeah. You're monitoring. You're lurking, yeah. Yeah. Oh, yeah. It's locked. Yeah.
Not even a little bit.
Okay. Yeah. If I can wire you up, yeah. The usual green on, not green off setup. So it's off right now. Just by,
All right, you guys need to move that clock.
We did I left the laptop here by mistake. Sorry. No worries. The wire's only so long, and a bunch of the outlets in the thing don't work. So I tried moving it, and it's less forgiving to shorter people. So yeah. I can give you a 5-minute flash if you want. If that makes you feel better.
It should be fine. I talk fast. So. Notorious.
I have a horrible feeling that no one is showing the kind of classic JWST GIF animation during this.
I took it out. I was going to, but
everyone assumes someone else will show it because someone always does, and it appears that finally is a tragedy that commons its way out of the talk.
Yeah, I took it out because it's only 13 minutes, right? So.
Yeah.
I suppose I could have just put it on my title slide or something. Next time.
Just slowly hypnotizing the audience and the build up to that.
Nobody would be listening to me; they'd just be watching me.
Yeah, it's mesmerizing. Have you seen Futurama where they have the hypno toad?
Yeah.
I feel like
totally. You need to put that sound in the background of it.
No, that's ATB harmonics. Oh, definitely. How are we for time? It's exactly 4 p.m. Okay, we're going to wait just 1 minute for the last people to trickle in, and we'll be getting started in about 30 seconds. Are we in? Where's the clock?
Yeah, do you want me to make it
Yeah. Yes, that's right. I think that's
Should I use this, Liz? Has it got the not? Well, I just haven't tried it. So. Yeah.
I think you have to really point it. Yeah.
Okay.
Hey everyone, we're gonna get started.
Yeah.
Please quiet down. Okay, great. Before we get into our first session, I just want to do a quick announcement about the Orioles baseball game. As some of you may have seen, they have now officially postponed the game to tomorrow. However, it's unfortunately going to be during our conference times. There's going to be one game at noon and then another game that starts at 3. And since we cannot bring our projector to the Orioles Stadium, we're unfortunately going to have to miss the game. We are going to try and get refunds for everyone. That is not generally their policy, but we're trying to fight for it so you guys can get your $12 back. But if not, then we will move the tickets to Friday evening. There's a game with the Washington Nationals at 7 p.m. on Friday. So if you're still around Friday evening, we'll send more details about that if that ends up being the option. We'll keep you in contact with what we end up doing. Sorry about that. I'm really bummed about it too, but maybe we can see baseball sometime in the future. Sorry, and just so we have like a social event interactivity today, I'm planning on going to Peabody Heights Brewery after the conference. It's a really awesome local brewery, and they have a really cool arcade in the back. So if you're interested in coming out to that, you can join me there. You can take it away, Chris. Sure.
Interlude for phase changes of volatiles in clouds to stellar deaths and ISM beginnings. Now bringing our tour to AGB stars with a talk from Martha Boyd. So,
yeah, thanks for having me. So I'm going to talk about AGB dust, and specifically AGB dust in the early universe. So I'm going to refute a little bit what Melissa said earlier today. That hopefully I'll convince you that AGB stars can be important at high redshift. But first I'm going to start with the local universe. So we know nearby that if you look at pre-solar grains, you get about 75% of those are coming from AGB stars. So AGB stars are dominating in the solar system. We know that if you go to M31 and you pick out the individual AGB stars and you count up how much dust they're making and compare that to the ISM, we think you could account for up to about 35% of the ISM dust. If you do the same thing in the Magellanic Clouds, where the metallicity is a little bit lower, we think you could account for up to half of the ISM dust, depending on the assumptions that you make. So clearly, AGB stars are prolific dust producers. They are really important to dust nearby. But the question is, what's going on at high redshift? So we know we have these massive dust reservoirs that are now being found in very distant galaxies out to a redshift of about 8. But models, AGB models, have typically predicted that metal-poor AGB stars just can't make enough dust to explain these dust reservoirs in these distant galaxies. And this is just a nice plot that I like to show from Rollins et al. 2014 that illustrates this issue. So they've got the amount of dust yield that you would need from the models to explain the ISM dust mass in one of these kinds of galaxies. And then they've got a bunch of different models that they're showing here, 4 different ones. And one of them gets kind of close, but the rest of them are well below that, and in some cases, an order of magnitude less than what you would need. So the solution for many, many years has been to invoke, of course, supernova dust and ISM grain growth. But if you notice here, the models, so they're all very different, and in many cases, an order of magnitude different from each other. And there's other models too that do the same thing. And I just want to point out that there's absolutely nothing wrong with any of these models. The problem is that there just hasn't been a lot of data to calibrate them with, and so we just don't, we can't constrain them. And so that's something that that I've been trying to do, and that my group has been trying to do for the last several years, is to build an observational database that we can use to actually find out what's going on in the data. So we started this a while back with Spitzer. We observed basically all of the nearby metal-poor galaxies that Spitzer could reach at 4.5 microns. And we measured the average dustiness of the stars in each galaxy and plotted that against metallicity here. And it's a scatter plot. So even at 1% solar metallicity, the stars in these galaxies are making, on average, just as much dust as the stars in the LMC and the SMC. So clearly, dust is forming very efficiently at these very low metallicities. But the caveat is that we think that probably most of these stars are low-mass carbon stars. So just to illustrate what that means, this is a plot of the initial mass of an AGB star. They go from about 0.8 to 10-ish solar masses as a function of metallicity. And the stars that are in the galaxies that we looked at with Spitzer are probably dominated by these carbon stars that live around here. So low metallicity and low mass. And these stars, they make a lot of dust because they make their own carbon and they dredge it up to the surface and they can make dust out of that. So they're very, very dusty. But we're interested in these guys. These are the massive AGB stars that could potentially be high redshift AGB analogs. But the problem is that these stars are oxygen rich. And oxygen rich can't make their own metals. So they rely on whatever pre-existing metals are there in the stars. And that is why the models typically predict that they just can't make a lot of dust. But if they could start injecting dust somewhere around 30 to 50 million years after they form. So we went back and we looked at those galaxies that we had observed with Spitzer using Hubble. And we did this in the near infrared using some narrow filters in the near infrared. And they are really good at separating oxygen-rich stars in blue from carbon-rich stars in red. And all the ones that are circled are things that look red in Spitzer, things that look dusty. And you can see from this, from the 6 galaxies that we looked at, that the dust is not limited to carbon stars. There are actually quite a few oxygen-rich stars in these galaxies. And I'll just highlight, these are low-mass galaxies. That's why you're only getting a handful of them. but they're there. And these are probably massive oxygen-rich AGB stars, and they're making dust at these extremely low metallicities. But we know basically nothing about these stars except that they look red at 4.5 microns and they're oxygen-rich. And that is where JWST comes in, because JWST can reach these galaxies and at much longer wavelengths with much more sensitivity, of course. So we decided to focus on this galaxy, Sextans A. We picked this one because it's one of the more metal poor ones in our sample, and it has some of the best dusty oxygen-rich stars over here. So we basically threw everything we had at it. This is what the galaxy looks like in the optical here. Here's our coverage with JWST. We got both NIRCam and MIRI coverage in many filters. And we also got spectroscopy from 5 to 13 microns of 6 of the stars. And just to orient you, the metallicity of Sextans A is somewhere between 1 and 7%. The 1% comes from measurements of the red giant branch stars, and the 7% comes from measurements of the ISM. So the AGB stars are somewhere in between that. So very metal poor. And this is the data, the photometry from NIRCam. This was put together by our fearless leader, Elizabeth Tarantino. And it's gorgeous. It's really, really deep. There's lots of really cool stuff in here. But we're highlighting, of course, the dustiest AGB stars in red up here. And when you look a little bit closer, you see that, yes, indeed, most of them are carbon rich, just as we thought. That's not too surprising, but they are really, really red. I mean, this one peaks at 10 microns, right? These are extremely red, extremely dusty stars. But the thing that was a little bit more surprising is that we're seeing silicate carbide in several of them. And we even have, for one of the stars that we have a spectrum of, we can see the silicate carbide in the spectrum. This is, the yellow one is the data. It's there, and its strength is similar to the strength that you see in the LMC and the SMC. So a lot of silicate carbide dust is being formed in this star, even though it's supposed to not, it's supposed to have very low metallicity. So that's sort of a surprise. We're getting these silicon-bearing dust grains in these very metal-poor stars. But let's look at the rest of the stars. So we're really interested in these guys, again, up here. These are the high-redshift AGB analogs. And these are our 6 spectra that we got. Most of them are carbon stars. You can tell from the acetylene feature. But we have this one oxygen-rich star. It doesn't have acetylene, and it has water, so we know it's oxygen-rich. We measured its luminosity, and based on that, we think it's about 4 to 5 solar masses. And also, based on fitting the color magnitude diagram of the whole galaxy, we think that the AGB stars are about 3% solar metallicity. So it is firmly in this box of being a high redshift AGB analog. So let's take a closer look. This is the SED of the star. The orange is the JWST data, and there's the spectrum. And this is all archival data over here. And we fit a photosphere of this to the star. And you can see that we have this huge excess in the infrared above the photosphere. But it's featureless, which is kind of weird, right? You would expect a dusty oxygen-rich star to have a big silicate feature, right? But it doesn't. And there's a bunch of different possibilities here. One possibility is that it's not dust at all. It could be what's called a water mole sphere. And this is basically just a sphere of molecular material. In this case, it would be water, because we see water in a couple of places in this SED. And these water mole spheres, they can raise the infrared excess in the SEDs, and we've seen them before in galactic stars and in Magellanic Cloud stars. But the problem is that they also come with features that we don't see. So we don't think it's a mole sphere. They could be playing a role, but it's not the dominant role. So we really do think that it's dust. Here are the options. Let me show you what those look like on the next slide. Okay, so we tried 4 different options. The first one we tried was amorphous carbon dust over here. And amorphous carbon dust would be a little bit weird to see around an oxygen-rich star, but not unheard of. You do have these dual chemistry stars that are out there, so it's possible. But the models just really don't fit. The best one was this blue one, and then there's a couple other options there in gray, but it always underestimates the flux over here, and it overestimates the flux over here. So we've ruled that one out. And we've tried large silicate grains over here. And large silicate grains we think are actually potentially important in AGB stars because they need to be large to drive winds. So it would not be unusual to see these. But here, first of all, you can't reproduce the overall excess without including a whole bunch of iron. And even with just 15% of these silicates, you still get a huge bump, even though these are pretty large grains. If you go to iron-rich silicates at a smaller grain size, it's the same story. You still get a big silicate bump, and in this case, only 5% gives you that huge bump. So iron really is the best fit. That's what's shown over here, and that's what we think we're seeing. And I'll zoom in a little bit. So now I'm plotting in Rayleigh Jeans units, so you can see the features a little bit better. The solid blue is the iron fit, and I just want to point out that we can't rule out a small amount of silicate dust based on these error bars, but if it's there, it's just there's only a few percent silicate. But the dust production rate from this model is actually really large. It's about the same as the average of the most extreme stars in the SMC. So, so it's really, really dusty. And that means that these stars are making a lot of dust at very low metallicity. And we don't think that this one is unique necessarily. We think there's maybe 2 or 4 more in Sextans A, but we don't have spectra. We only have photometry of those. And this has, not only implications for how much dust might be produced in the early universe, but possibly also for the dust mineralogy in the early universe. And just to sort of summarize what that means for the early universe, this is a plot from a review paper last year showing the contribution from supernova and AGB stars. So the dark blue are supernova without the reverse shock. With the reverse shock is the light blue, and in 2 different metallicity ranges. And then the dark yellow is metal-rich AGB, and the light yellow is metal-poor AGB. And the models have shown that because of this delayed injection of carbon stars at low metallicity, they don't start to meet supernova at the lowest metallicity end over here. They don't start to meet supernova until like redshift 5 or 6 or so. But these models only include silicates and carbon. And so if you include iron, the line might look a little bit more like this dark yellow one, like the metal-rich AGB stars, where you get an earlier injection and potentially could meet the supernova maybe around redshift 10 or so. But we don't know. So that's basically it. The summary is just that these data show very dusty stars in Sextans A, even at this extremely low metallicity. We're seeing metallic iron dust for the first time as a sole type of dust in this star. And this has implications for the mineralogy at high redshift. And I also just want to highlight, we only have 1 star like this. We've seen iron in other stars, but they always come with silicates. And this is the first time we've seen one where it's just iron only. The only stars like it are a handful of stars that we've seen in globular clusters that are very low mass, like 1 solar mass. And so those aren't high redshift AGB analogs, but we know that this star is not totally unique. We have seen others sort of like it. But I would just urge that we get more data of metal-poor galaxies so that we can build up the sample and try to understand what is going on with these massive AGB stars at high redshift. And that's it.
We have questions for Martha.
Thank you very much for the very interesting talk. So the question is related to where the iron comes from, because in typical chemical evolution, then iron is from the supernovae. So is it then that the AGB star has accreted something that allowed it to form the iron as efficient as it does, or is it?
Yeah, there's actually enough iron there to make this dust. The models that we use include abundances, and they have dust growth in them. And you can actually make this much iron dust without condensing all of the iron. There's plenty there. It was just never included in the models because the assumption was that there would be way more silicate dust or carbon dust for a lower mass star. Right? Models do include iron of AGB stars, but the ones that they apply to high redshift typically don't include them. Yeah.
Hi, Martha. So I kind of missed this, but if these are 4 to 5 solar mass stars, that means that their timescales are like, wouldn't that be closer to 100 million years then?
Yeah, this one is about 4 to 5 solar masses, but it is representative of that higher mass and range, these hot bottom burning AGB stars that range from about 4 to 10 solar masses, and they all have sort of a similar evolution in that range. And so, so yes, this one is on the lower end of that range, but it's within that in that window.
Is this present day mass or was this the initial?
Yeah, I mean, Sextans A is, yeah, it's present day dust right now that we observe in Sextans.
I meant the AGB star that you said is 4 to 5 solar mass. Is that present day?
Oh, birth mass.
Birth mass.
Yeah.
Carl?
No. So I'm intrigued by iron dust, right? Because there's got to be some iron dust in the ISM. We just don't have a feature usually. So I guess my question is, has iron dust usually been considered when you're fitting the AGB stars? And I guess another way to state it is, how much iron dust could be produced in the Milky Way or the M31 or the Magellanic Clouds that we just haven't accounted for yet?
Yeah, I mean, for a long, long time, people have been using iron to boost the overall excess in their SED fits because silicates alone can't do it, right? So iron, people have been fitting iron to their stars for a long time. It's just usually a smaller fraction compared to the silicates. But here, we only have the iron, and it's the only massive AGB star where we've seen that. Yeah.
Pretty quick. So the models, Martha, that you were showing at the beginning of the talk, right? The different models of the AGB dust production, sort of following up on Carl's question, how much does this boost you up, this kind of production?
It's really hard to say because it's one star. So I mean, I've looked at the models from one group, and it looks like this star might be making, maybe a factor of 2 more dust than they predict, but we don't have an exact mass for it, and it's only one star. We don't, and the metallicity of those models isn't an exact match, so it's kind of hard to say, but it's possible that it's making more than at least those models predict. But we really need more data to say anything conclusive. Yeah.
On the tragic note of more data wanted. Indeed, I think we should thank Martha again. Switch it on.
Is that loud enough? Loud enough? Okay.
I just think your time will be down there. And next up we have Siddhartha Vasan, who's going up the coveted title of most contrived acronym in the Symposium, talking about rainbows. So over to you.
Thank you. I'd like to thank the organizers for accepting this horrible acronym first as a poster and then upgrading it when they saw it was horrible. Really, the most thought that we put into the abstract was coming up with this horrible acronym. So you just heard about AGB stars at z equals 6 to 12. I'm going to tell you a little bit about AGB stars right now. This is part of the Nearby Evolved Stars survey. The PI of the survey is Peter Scicluna, who's now at Hertfordshire. And we have a couple other people who've been working on some papers that I'll tell you about. Alfonso Trejo is also at IRIA, and he is working on the ACA data. Sophia Wallström, who has now left astronomy, but before she did, she analyzed the JCMT heterodyne data for us. Ian McDonald has been working on the catalog paper, and Tavisha has been part of the Gaia team, and she's been working on the 3D dust extinction, just in general, but her results are applicable to us as well. Okay, so I don't have to tell you, right, why galaxies care about AGB stars. Well, very quickly, there's many of them in present-day star-forming galaxies. Because of the fact that they have nucleosynthesis and dredge up, they can generate quite a bit of nucleosynthetic elements that they transport to the surface, where it forms molecules and dust, and those molecules in that dust is blown out. About 80% of the initial mass, up to 80% can be lost. And like I said, this mass loss is dusty as well. And as Martha already pointed out, in present-day galaxies, they are non-negligible contributors to the dust budget. So again, horrible title. Why study and where study? So where study AGB stars? Well, here's a cartoon here. You can study it anywhere. And in fact, the NESS survey, this is the idea that we had with NESS, is to get as much data as possible over as many, to study as many physical scales as possible. And we started with the submillimeter, where you can study old and gold dust and see rotational lines. And we also now have some radio data. Of course, these sources are very close by, so quite a few of them have been well studied. There's archival data at a lot of wavelengths, especially mid-infrared, optical, of course, near-infrared as well. And well, while we're working on this, we discovered, we thought about the fact that we have models that predict what happens with the high JCO. So with the high JCO profiles, the shape can tell you something about what's happening in the acceleration zone. So in fact, PRIMA could be used for this as well. Okay, so what's great and what's difficult about studies in the Milky Way? Well, foreground extinction is the problem. So we have uncertain distances to these sources, which means that the luminosities are not constrained. When I flashed this in Heidelberg, they were like, really? So yes, the parallax uncertainty in DR3 for the nearest AGB, well, we don't know if it's the nearest because it's a 40% uncertainty, but yeah, that's 90 parsec and that's 40%. So this happens because of various properties that the AGB star has. Of course, dust obscuration, but also pulsation and convection, and that results in imprecise parallaxes. And time series Gaia data in DR4 might help with it a little bit, but of course, then you're not looking at the dustiest objects. That will still require something in the near-infrared maybe. So the workaround that people have had in the past is to, instead of looking at larger samples, look at compact populations, so the bulge stars. As Martha pointed out, Steve has a paper recently working on this as well. Or you can do small bias samples. You can look at only the carbon stars, only the optical stars. Or you can look at larger samples as long as you're happy with lower detection rates, and that's also been done. The problem there is that the selection is not homogeneous, so you also have to account for stochasticity, large spread properties, which we know happens. For example, the AGB community has been using the gas to dust ratio of 200 forever, and as it turns out, once you start actually looking at individual AGB stars, the range is huge on that one. So we were trying to look for how can we best make a volume complete sample. Of course, we don't know the distances, but still, how best can we approach this problem? So this was already approached in the late 80s and early 90s. And what they did was they assumed that assuming a typical luminosity for the AGB star, you come up with a luminosity distance, and then you can pretend that you have a volume complete sample. Now that we have parallaxes, even if they're not precise enough, we can improve upon this. And also, thanks to the studies in the Magellanic Clouds, we have an idea of the luminosity function. So instead of using just a 10,000 solar, we can use the mean, median values of the luminosity from the Magellanic Clouds. And that's what we did to select our sources here. So we have about 800, I think it's 852, although one of them is duplicate, so 851 sources. It was originally the luminosity distances were calculated and then we cut it off at 3 kiloparsec, but now it turns out, having updated the distances, that we have some sources that go up to 5 kiloparsec. The original selection was based on IRAS colors, and we determined selected dusty sources that might have dusty mass loss. Most of them did turn out to be AGB stars, but we do have about 70 sources contamination in there, YSOs, things like that. The AGB sample definitely contains both the most evolved population as well as early phases of mass loss as well. In addition, there's about 500 sources, and there's an overlap here within 300 parsec of the solar neighborhood. So there's a bunch of papers here. I'm going to talk about a few of them. And also there's a lot of archival data, again, at a lot of wavelengths. We also have light curves, which is a different story altogether. So this allows us to study the mass loss in the gas and the dust, and also the mass loss history in the shell. And as a comparison, there are two other surveys, ongoing surveys. So they sacrifice sample size for higher resolution. And there's quite a bit of beautiful work done with these surveys. So, okay, so this is the wedding cake figure for the nest sample. There's a bunch of tiers based on what their estimated dust production rate is, but what you're seeing here in the background is the original distances for these sources, and they've been updated. And so now this is our new sample here. We've also eliminated, like I said, about 70 sources as not being AGB stars. Okay, let me tell you a little bit about what we've done with the data we already have. I'm only going to have this slide talking about the dust. Everything else is about the gas. So back in 2019, Tavisha had published a paper where we analyzed the extended dust envelope. This has already been done with near-infrared, far-infrared, and ALMA wavelengths. With the JCMT, you get full dish data, single dish data. So you're sampling the entire, all the spatial scales. So these are a bunch of models that we fit. So this is a simultaneous fit that takes into account the optical, the near-infrared, far-infrared, and the submillimeter as well. And that excess is real. So there's something in the submillimeter dust properties that is different. So that's TBD. We have, for the gas envelope, we have more data as well. I think we also have VLA data that's incoming. But these are the 4 things I'll just show you, flash just a few, let's see what time. Okay. So this is the JCMT heterodyne data. There are 3 kinds of spectra that we see, spectra shapes. So if you have a spherical constant velocity expanding shell, then you should see a soft parabola. But we also see these 2 here. So the constant velocity spherically symmetric soft parabola is the majority of the sources here, but there are some sources that have multiple velocity components and some that are asymmetric. And this is not surprising. This has been seen before, and people have tried to model this. So the idea is that this is what we have to keep in mind when we're trying to model these sources. This is the NRO data. So the black curves here are the NRO data. That's the CO2 to 1. This is CO3 to 2 from the JCMT, and this is the 850 micron dust continuum. So you can see that the 2 to 1 is quite, the extension is seen in actually most of the sample here. It's a much smaller sample. It's about 25 objects, I think, but yeah, we see the extension in most of these. They've also found that the 12 to 13 ratio varies with radius, which means that there is selective photo dissociation going on as well. LMT data. All right, so some people were excited when I said I had LMT data because nobody's been able to figure out what's going on with this thing. Well, we applied for this thing back in 2022, I think. And for AGB stars, after having read the manual, we thought that, okay, well, the position switching mode is the one that allows efficient mapping of the AGB star. After about a year, maybe, we heard from them saying, oh, actually, that mode has not yet been commissioned. So we'll just give you the regular mode, which results in, for the same time request, I think about √3 worse signal. That's what we have now. But that's UANT there. You can see the detached shell right there. So at least we have some data. This is fresh. We just realized about 3 weeks ago that this data is ready. So we have to go look at that soon. So this is 1 to 0. That samples the most extended parts of these AGB stars. Okay, now that I have that, on to the modeling of the gas and dust as well. So first thing is that we have to get constraints of the photosphere and what's happening very close to it. This is work that I did a long time ago, which basically showed, so this is a carbon star of the LMC here, which does not have a lot of dust. This one does have dust. What we did is we just took this source and added a black body to it for the dust emission. We showed that basically what happens is the CO feature gets filled in. So that's something we have to account for, which in general is not accounted for when you take near-infrared spectra and try to figure out the effective temperature in log G. So this is another thing we know we have to do. We have data from the JWST optical telescope in India, which I think they finished taking earlier this week, so have to go check that out. That'll give us more fodder to work with. All right, so we have done that. In the near-infrared, though, you still do see the gas features, especially you see more prominent C2H2 features for dustier sources. So we have modeled that in the past with a slab, but it looks like because there are issues of constraining the location of the emission, we need to model both the gas and the dust all through the shell. So this is an experiment I had where I had a grid of dust models, I have a grid of gas models. I combined the two together and trained a neural network to take these three sources, which Greg published last year, and I tried fits with these. And interestingly, I find that the black are 100 posterior samples, and I find that we find really good fits to the C2H2 feature for the dustier objects. That's very interesting. Again, this is just a practice thing. We have to work on it. So here, I spent 2.5 months fighting with the SGR code. Why? Well, we have two options, SGR and RadMC3D, which people seem to do because it's three-dimensional. I'm trying both. I tried SGR because nobody's tried it for AGB stars, and it's well documented. So I just wanted to try it out. I am successful. I got some CO lines there. I got the SIC feature over here. And of course, this is for 10 to the 6 photons, so there's a lot of noise there. So that means that I just have more work to do. But yay, I did something. And now the hard part. I have to do many, many more things, including incorporating dynamic photosphere models, which means we'll have a better idea of the variability of the molecular features as well. Yeah, and of course, developing a model grid. So perfect. That was basically it. I'm just going to put this up again and thank the organizers and the public as well. Thank you.
So assuming the voice is Steve, is there a person you can mute?
I cannot.
Gary?
Kevin?
Now someone
Jail, if you could please mute.
Thank you.
It's not helping.
We're gonna. There we go. Oh, thank you so much. There we go. Okay. Any questions other than the ringing?
As a fellow LMT fan, I wanted to hear about, so you got position switched. You could have gotten position switched data, but you had that beautiful resolved external shell in that one source. Would you have been able to tell that you had that detached shell with just a position switch measurement?
I don't even know. Like, I tried asking. It is so difficult to get information out of the LMT people.
It is improving, but yes.
So do you know if PS is already commissioned?
I have PS data, yeah.
Okay.
It is working.
You can switch off that, maybe and switch to the podium mic.
Yeah, sure.
Right.
There we go. That's better.
You have an online question?
No.
Oh. Is that you question? Oh, okay. I'm curious about your ACA data and the spatial distribution. Do you see any other patterns in the rest of your data in those specific sources that don't seem spherically symmetric?
What kind of patterns?
Either from the pulsation data, photometric data, spectral data.
So this is where we're going. We have I just spent the last month and a half only analyzing the ACA profiles, but this is where we want to go. Yes, and that's why I was talking to you earlier. Yeah.
Great talk, thank you. You, I think, briefly mentioned in one of your spectra you had a CO absorption feature. I think it was at something like 2.27 microns. And I think you said, you said that could be due to interstellar CO, but that feature also occurs in low temperature stars.
Sorry, I was going very fast. What I meant is that this is circumstellar dust that I'm accounting for. So what I meant is that the CO features arise due to the molecules on the near the stellar surface, and then the dust, which is further out, extinguishes them. So that this was just a test to demonstrate that in dustier sources, you can get it by taking a less dusty source, adding dust emission to it. So it's circumstellar dust emission.
Okay, thank you. I think it's time to move on. So another round of applause for Sunda, please.
Yeah, try the other one.
Try the other point. All right, take that off you. Okay, look. Green. Okay, fantastic. Your time will be on the thing there.
Is the point?
Point him at that. It should then the slide should change. Yeah, there we go. Fantastic. So for our final talk today about the final part of Stellar Lives, we have Maya and Saberi. So take it away. Thank you.
Thank you. Good afternoon, everyone. My name is Mayam Saberi, and I'm a researcher at the University of Oslo. In this talk, I'm going to give you a very brief introduction, and then I'm going to talk about 3 different ongoing projects very briefly, which I'm currently doing to understand the recycled material from nearby AGB stars into the ISM. As it mentioned earlier, AGB is the late phase of evolution for stars with initial mass of 1 to 8 solar mass. And as we saw this diagram before, in the HR diagram, AGBs are located in the upper right, which means they have a cool temperature of maximum 3000 Kelvin, but they are very luminous. But the most important characteristics that makes us interested to study this specific phase of evolution is their huge mass loss. At this phase, the star loses up to 80% of its initial mass, which means it ejects all the synthesized heavy elements and stellar dust to the ISM. So they heavily contribute to the enrichment of the ISM and galaxies. As one of the consequences of this huge mass loss is the formation of this beautiful circumstellar envelope around the star. And studying these circumstellar envelopes provides us a great opportunity to understand the recycled material from these stars into the ISM. Here I'm showing you a schematic view of the CSC around the giant stars. This envelope is really large, is 100,000 times bigger than the star itself. So there are different processes which control the chemistry at different parts. In the inner CSC, where it's close to the star, we have pulsation and shock chemistry. And in the intermediate, we have dust formation, and this is where the gas starts to accelerate. And in the outer CSC, this is where the circumstellar envelope meets the ISM. We have the penetration of interstellar photons. So this is like a PDR region. And thanks to ALMA, we are able to observe the molecular abundance distribution of various elements at different parts of the CSC and understand the chemistry which is happening as a different part. As you can see here, this is like shows the ALMA beam at 800 gigahertz, which gives us a resolution of 0.02 arcsecond, which I'm going to show you more of ALMA observation later. So this brings me to the first project I'm currently doing. In the first project, I aim to understand the origin of element fluorine in the periodic table. Fluorine is among few elements in the periodic table which its origin is unknown. From theoretical studies, there are some sites proposed to produce the galactic fluorine. These are like during helium burning flash in AGB stars, neutrino process in supernovae explosions, a merger of between helium and carbon oxygen white dwarfs, helium burning in Wolf-Rayet stars, and rapidly rotating massive stars. And among all these sources, AGB stars are the only one with some observational evidence. In all the studies where people were looking to observe fluorine in the galaxy, all studies were focused on observation of HF lines in infrared. This is one of the most famous studies from Urison 1992, where they estimated an overabundance up to 3 times of the solar value. However, these HF lines are largely contaminated by telluric lines. So there are a lot of discussion about the accuracy of these studies based on HF lines. Then later in 2005, Werner, they reported UV observation of ionized fluorine and then in post-AGB stars. And then they reported overabundance between 10 to 250 times of the solar value. And they claim this overabundance in fluorine observed in post-AGBs is the fluorine which is produced during AGB phase, and now we can observe it in post-AGB. How we got interested? I had some ALMA data during my PhD. I found 5 ALF lines in the data, and then I looked at the chemical models which shows the chemistry of fluorine in the circumstellar envelopes of AGB stars. Here you can see the molecular distribution of all molecules that contains fluorine in the circumstellar envelope. And as you can see here, excuse me, this should be ALF. In addition to HF, most of the fluorine is locked into ALF. So we thought maybe ALF can be a better tracer to measure the fluorine in AGB stars rather than HF. Then I looked at ALMA archive, and I found that, that there are some more sources with ALF detection which has never been published. So we decided to do a paper on that. We calculated the ALF abundance in all the 5 sources, and we estimated in all the 5 sources the fluorine abundance is very similar to solar abundance. So there is no overabundance in the sample we had. Then we looked at a stellar yields model. In the stellar yields model, they show that the fluorine enrichment is a strong function of initial mass and metallicity. About the metallicity, here in this plot, you can see the yields of fluorine for different initial mass and 3 different metallicity. In order to do observation to see how accurate are these stellar yields models, we cannot really trace the metallicity because the abundance is so low. So we are limited to nearby AGB stars where we assume they have solar metallicity. But if we manage to find stars with different mass, then we can see how accurate these yields models are. And the sample that I had, the 5 sources that I just showed you, they are all low mass AGB stars with initial mass of 1. So our result is kind of consistent with the stellar yields model. So we tried to put another proposal, finding AGB stars with initial mass between 2 to 4. And the aim of the project is to quantify the role of AGB stars in the total galactic total fluorine budget in our galaxy. We only managed to get 3 sources observed, and my postdoc is currently analyzing the data, so stay tuned. The result will be published in Sgr A et al. The next project that I want to briefly talk about is again ALMA observation of a nearby AGB star, Myra or Oseti. We have band 6, 7, and 8 observation. Here I'm just showing you a small part of data from band 8 to show you how many lines we observed. It was crazy. It was a forest of lines. And among these lines, I noticed that we have observations of all 5 isotopes of titanium dioxide. Which was interesting. So I did this population diagram. This is the main isotope, and these are the rare isotopologue. So we calculated the column density, and we estimated the titanium ratio and compared it with solar values. For all ratios, we have a slight moderate overabundance compared to solar. Then we compared this with S-process prediction, and we saw that it really matches. the prediction from S process. So this means that, and this observation were not meant to do this study. It means that the ALMA sensitivity will allow us is going to be very useful in studying nucleosynthesis in AGB stars, and this can also be used in the isotopic ratios where we are in doubt that the changes in the isotopic ratios is due to a stellar evolution versus galactic chemical evolution. So now I'm going to the last project I'm going to talk about. This is my favorite project. I left my favorite, like the best part to the end. In this project, the aim is to study the impact of internal UV radiation on the circumstellar chemistry. This is the schematic view I showed you during, when I started my presentation, but this is not a complete picture. And you may ask, this star, I mentioned that they have a surface temperature of maximum 3000 Kelvin. So what UV radiation are you talking about? The UV radiation is coming from either binary companion, because most of AGB stars have hot main sequence or white dwarf companion, and or they show a stellar chromospheric activity, which has been ignored in all chemical models of AGB stars, simply because it's so complicated. But we think this internal source of UV can hugely disturb the chemistry here, so and it's important to be considered. And in addition to this, yesterday we saw from Hannah's talk, she showed us the 3D model of local ISRF, and she showed that it can change by a factor of 1,000. However, in all models of AGBs, we consider a standard interstellar radiation field. So this is also really, I'm so looking forward to get results and to implement that to see how much it impacts the chemistry of the outer CSCs. Here I would like to show you some observational evidences of internal UV radiation that we have so far. This is the GALEX. There was a GALEX survey of a large sample of AGB stars, and in the GALEX survey, they detected a strong UV radiation in 57% of the sample. And they also did some low resolution spectroscopy for a few samples. And in all of this, we saw C2 and magnesium-2 emissions, which was kind of chromospheric tracer lines. Before this GALEX, we also have some HST observations of a few nearby AGB stars. Here you can show a part of data for our LEO. We have beautiful C2 emission lines, which are a tracer of electron gas density, which is needed in order to model even the observations that we get from ALMA. I will show you in a bit. And the most recent observations are done with ALMA. These are ALMA observation of two close by AGB stars, and here we see these hot spots which are dynamic, and the surface temperature of this hot spot is 53,000 Kelvin, while the star itself is very cold. And so it means that it's really important to consider all this shows that it's really important to consider the internal UV radiation which impacts the circumstellar chemistry. To study this, I am currently working on HST UV observation of RLEO. This is we have this beautiful spectra. 200 lines are detected in this spectra. Here you can see all species that we have with the number of transitions. Here in the red, this is our preliminary modeling result for FE2 lines, which we have like 130 lines. Yeah, but it turns out that actually this is a lot more complicated than what I expected. Unfortunately, we have only observation, this kind of observation for one source, which is RLEO, but we are trying to get more data on this. With this, yeah, I just conclude my talk. In the project number 1, we are aiming to determine the contribution of AGB stars in the galactic fluorine budget, and eventually going to observe the other candidates in UV, because those are not observable. The hot sources, they don't have molecular gas, so we need to go to the UV. In project 2, we show that ALMA technical capabilities allow us to distinguish the impact of stellar evolution versus galactic chemical evolution for the isotopic chemistry of titanium. And overall, this kind of observation shows that although ALMA observation has significantly improved our understanding of the circumstellar chemistry, we still need more UV observations to understand the stellar shocks and dynamic chromosphere in these cool stars, which has been ignored. And yeah, this is needed to understand the recycled material from solar like stars to the ISM. Thank you.
All right, questions for Gaia? Jumping first with using the chair prerogative. I had no idea fluorine was such a mystery. That's fascinating. For the aluminium fluoride, I guess, bodices, does that also depend upon the yield of aluminium from those stars as well?
No. Yeah. Yeah, it's mostly is a mystery because it has only one stable isotope, and it's easily destroyed during stellar evolution. And if you saw in the yields model that I showed, if the star has or more massive than 3 solar mass, it gets destroyed during hot bottom burning. And when they are too low mass, they are not efficiently produced. So it's like very, at least in the AGB stars. But the other sources, I'm not aware if there has been any attempt to constrain the amount of fluorine that comes from other sources. We cannot do this with observing molecular gas because they are just hot and all the molecules will be destroyed. So the way is to go for ionized fluorine observation, but I'm not aware if there's any attempts. Yeah.
Could you show us the W hyperon?
Oops. This one?
Okay. I think I see something in the LFP data. We can talk about it.
Okay, cool, sure.
And then Nick over there. You had the plot of the dominant fluorine reservoir, and I was intrigued that it switches from HF close to the star to ALF farther out. What's the chemistry that drives that?
Actually, if you...
I have it backwards.
Oops. Yeah, here. Here the model is only from 1 to 10 stellar radii. It's so very limited. Unfortunately, in these models, they have not done like further away. Oh, your question is that what switch HF to ALF, yeah. Right? Sure, actually, about that.
I'm just wondering because I know in the ISM we see HF, but I don't know that ALF has been observed in the interstellar medium.
Okay. Yeah.
More questions?
I know almost nothing about stars, so I would have naively, I'm thinking about your 60% of AGB stars have detected UV. I would have naively thought that a dust producer would obscure its own internally produced UV unless the envelope has holes in it. Was it accounted for? Is the measurement consistent with they all have it? And you just don't see it sometimes?
That's a good question because I think it has been like the internal UV radiation has been like historically ignored because like first dust and also these are cooler stars. But this the thing is that this UV that we observe, this is the one which passes through the dust, and we don't have a good models about how much dust they have. So it means that they actually have really a strong UV radiation. So this is like the observation we have. This is, of course, it passes the dust, but it still it's very strong. Yeah. And it's really interesting that they also have like chromospheric emission, but we really, because like obviously solar physicists have problem describing the chromosphere of the sun, so it's like natural that in evolved stars community they all ignored because it's just simply so complicated.
Final question? Okay. If not, round of applause. Any final words from?
Yeah. Before the day ends, I'm excited to stop talking about the Orioles baseball game after this announcement. We have been able to get a refund for the tickets, so you guys should get it back. I just want to have a huge thank you to Hannah Bish. She will be going through all of the 150 tickets by hand and delivering you your refund by hand. So please
buy her a drink.
Buy her a drink. Have some patience for her over the next week or so, for her to return the tickets. Sorry it didn't work out, everyone, but I hope we can have fun tonight at Peabody's or anywhere else that you want to go and enjoy the rest of the week at the other social events we have planned. Thanks, everyone. Enjoy the rest of your night.